If you take any problem in mathematics or applied mathematics and you understand it and work on it and eventually make some progress and come up with something interesting. Turbulence is the exception.
Is turbulence solvable?
Well, I'm sure it is, but the question is how? And what's missing is some fundamental new idea. So at this point, people try eating at the edges of the problem, but it's not making enough progress. Chaos was a new idea. Chaos explained how come you can have a random phenomenon in deterministic equations, and therefore it provided an insight. But it has not helped solve the problem because what you can describe well by chaotic dynamics and turbulence is still laminar. Turbulence is much more complicated. So, but that was a new idea. One needs some other new idea which will actually allow you to go into the turbulent regime, and it's not there yet.
Do you think that new idea will come from mathematics or statistics, or what has to come into play?
Well, the problem of turbulence is a mathematics problem. The equations have been known for a century and a half. No one has any doubt about their validity. So the problem is solving it.
It also is a surprise to people to discover that data isn't always true.
Yes.
There's errors, there's misunderstandings, there's inaccurate experiments, there's poor measurements, there's all sorts of things.
Well, in fact, this work I've been doing of late about data assimilation is a way to try to clean data, get data which are unreliable and models which are unreliable and try to conclude from them something which may not be completely false. Just about all the software that's being used to make any kind of prediction depends on some mathematical assumption. Even trying to draw conclusions from data is at this point a mathematical question which has not been properly addressed and has not been solved.
Alexandre, so give us some history, if we could, as life before you became a mathematician. Where were you born, and tell me more.
Okay, I was born in Warsaw in Poland, and 15 months after I was born, Hitler invaded, so we ran. And we came to get to Israel in 1941 through some very complicated route through Russia. And and my earliest memories are from Israel. That's my place of origin.
How long did this take, from leaving Poland to ending up in Israel?
It took 2 years.
So where in Israel?
Tel Aviv. We lived in Tel Aviv. Actually, my first memory is the Italians bombing the sea.
All right.
The Italians used to come and Italian bombers used to come from Rhodes and didn't want to risk themselves over anti-aircraft fire, so they used to drop the bombs into the sea and go back home. And everybody used to go and watch. So that's my first memory.
So what was your first language?
My first language was Polish, but I learned Hebrew very soon afterwards.
Was Polish spoken at home in Israel?
Yes. My mother never learned Hebrew, so my mother and I spoke Polish until I learned French, which is years later. And my father learned Hebrew quite quickly.
But she lived in Israel but did not learn Hebrew.
Right.
Was that easy to do?
Not learn Hebrew?
Yes.
Well, the neighborhood in which we lived was entirely Polish-speaking. The grocery stores spoke Polish. Everybody spoke Polish. The problem came with school because the teachers didn't speak Polish, so my mother could not communicate with the school teachers. But it was very easy. It was lots of refugees in Israel at the time. Each one they tend to live in neighborhoods in which the language was familiar.
So then, where did French show up?
When I was 12 years old, we moved to Switzerland, and that's where French showed up.
So this was before English?
Before English, yes.
Why Switzerland?
That's a good question. I don't know the answer. I guess family reasons is the best explanation. I'm not quite sure what the answer is. But for me, it was a big blow. I didn't like Switzerland. I didn't acclimatize myself there well. And I kept asking throughout my adolescence, why are we in Switzerland? I didn't get a good answer.
Did you travel back to Israel when you were there, or is it now we're in Switzerland and we're staying? So Switzerland was what we would call junior high school and high school?
College.
Okay. So You chose to go then to college in Switzerland.
I had no choice because my parents got ill, and then since they were quite isolated, I was needed at home. So that's somebody had to take care of doctors and stuff, and so I couldn't go back. In fact, I was supposed to go to serve in the army, and they let me stay until I finished college because of the home situation.
Where were you in Switzerland?
Geneva. I went to high school in Geneva, and I went to college in Lausanne.
College was mathematics or what?
Let me tell you about mathematics.
Okay.
So if you had asked me when I was like 9 years old or 8 years old what I wanted to do, I would have said I wanted to be a mathematician. My parents had a friend who I think was some kind of distant relative who had a PhD in math. And he started coming and asking me math questions when I was, as far as I know, in kindergarten. Not very hard questions, not real math. One which I remember was, suppose you have a sidewalk 12 meters long and you plant a tree every meter. How many trees will you plant? Some things of that kind. And he was telling me I should be a mathematician, and since I enjoyed the attention and the questions, that's what I would have said. And so that's the idea. And then in Israel, when I was 10 years old, they put me in some kind of gifted program, and the idea was I'd skip grades. A grade a year for a while until I could go to college at an early age. And I skipped 2 of those grades. But then we moved to, and the idea was I'll be a mathematician to go and study math. But when we got to Switzerland, this was lost, I think, fortunately, because I know lots of people who came to university early and they don't, in retrospect, they regret the experience. But Switzerland, I was not a good student. I didn't do so great in high school. And the whole idea of my being gifted and doing math got lost a bit, except that I still wanted to do it. And I went to college in engineering because it seemed to be the closest thing to math at which I could make a living.
What kind of engineering?
I started in mechanical engineering.
So is this theoretical engineering, or is this sitting on the floor in laboratory experiments?
The way this is organized there is the first 3 years were theoretical, math, physics, very enjoyable. And the last 2 were sitting on the floor making experiments, which I enjoyed much less. But I shifted from mechanical to what was called physics engineering, which is applied physics, after what would be the first degree. So I have by American standards, I've got a degree in mechanical engineering, an undergraduate, bachelor's degree, and a master's degree in applied physics.
Do you keep in touch with any of those classmates? What did they go off to do?
I know what they do because there was a 50th reunion last year, and I know from the list they sent me what they do, but I didn't keep in touch with Lausanne very much. I wasn't happy there. I didn't make friends. I wasn't happy there, except the college was fine. In fact, they gave you a very good education.
You're graduating and you're trying to figure out what to do next.
Okay, yes.
What did you do?
Well, at the time, it was obvious what I had to do next. I had to go back to Israel for military service. So I wasn't looking for anything else. But while I was in college, it became clear to me again that I wanted to be a mathematician. I did very well in college. And I fell into the orbit of Durham, who was a very famous mathematician there, and took a variety of geometry and topology courses. So by that time, if you'd asked me, I probably would have said I wanted to be a geometer. And so, but certainly math was something which I wanted to do. Even in high school, even though I wasn't doing so great, if people asked me what I wanted to do, I would have said mathematician. So let me say something about Durham first, because again, the Durham also had a very big impact on me, in particular because my experience in high school, which is basically negative, and my being in engineering school to a large extent because I didn't have the possibility of studying mathematics and not confidence that I could. In that situation, the fact that he seemed to be singling me out for high grades and praise, and taking seriously my desire to be a mathematician was very important. And in later years, of course, he gave me lots of very good advice. He's the one who basically sent me to grad school, arranged for it. told me how to go about finding a grad school to go to and how to and a fellowship.
You have to go back to Israel then and join the army.
Yes, so I went to Israel. It's complicated, so I accepted to be drafted and serve in some kind of infantry, but ended up programming at the Weizmann Institute. And
what year is this?
This is 1961.
So what are you programming?
So I programmed a variety of fluid mechanics problems and a variety of things we were doing on Grant. I did some programming for some tidal motion project. I did some programming for some other hydrodynamics problems. And I must say that I didn't like the Weizmann Institute so much. I wanted to get more degrees. But I absolutely loved the computational fluid mechanics, computational physics.
What was the machine?
They had a home-built computer. The U.S. would not sell Israeli computers because they were afraid that they'd use it to build a bomb. So the Israelis built their own computer, which is called the Weizsack, which was, of course, they used it to build a bomb. But so I was working on the only computer in Israel.
What did one program with?
It's machine language on paper tapes. You get the tapes, you just have to read them like this. And so when the IBM cards came towards the end of my stay there, this was big progress.
Do you remember any of the algorithms?
I remember quite vividly the algorithms. Of course, they're prehistorical. But I programmed relaxation algorithms. I programmed Runge-Kutta stuff. I just programmed standard numeric analysis.
And how did you know those algorithms? From your mechanical engineering training or just reading?
Well, there was some training there, some bit of training, and I read up. And of course, some of my colleagues there were very knowledgeable. And so I keep in touch with those people quite well. I also keep in touch with childhood friends from kindergarten and grade school.
What was a fluid mechanics problem that was state-of-the-art in 1961 to try to solve?
Well, the one that the programming for was solving the Laplace equation of the tides to estimate the height of the tides in the global ocean, which is a gigantic linear algebra problem.
Why was that the job of somebody in the Army?
Well, I was in the Army. It's a complicated. I don't want to explain the whole machinery because it's complicated. But basically, I was actually working for a civilian project funded by the U.S. Air Force, because the motion of the tides has an impact on the motion of satellites, which affects how you communicate with them, how you aim beams at them.
I can't help but point out that you're working on a grant funded by the Air Force, but you're not allowed to own a U.S. machine?
Right.
Okay. All right.
The logic is not.
Yeah, okay.
Okay. Then I decided I became very strong in the conviction that what I wanted to do is some kind of computation to do with math and physics and differential equation. I just loved those calculations. So I applied to the Hebrew University for admission to the math program, and they gave me an interview. They admitted me, and they told me that what I want to study, they don't teach. And they advised me to go abroad. I wrote to Paris, and they admitted me to some program, conceivably Lyon's program, I'm not sure, but I couldn't fund it. And then Durham advised me to apply to American universities, which I did. And when the admissions came, he advised me to go to Courant, of which I'd never heard before. In fact, he was more specific. He told me to go to Courant to work with Peter Lax. And so I did it. It helped that NYU was enthusiastic about getting me. I applied on a Monday, and I got a response in a week. Monday afterwards, there was a letter with admission, which is amazing. Nowadays, it's inconceivable because the mail is slower. I guess not email. So anyway, so I went to Courant, and that was a very good. I was very happy.
Was that your first trip to the U.S.?
Yeah, of course.
How did you get there?
At the time, the cheap way of getting to the U.S. was by boat. And they had student boats, which left nothing but students, which left ports in France and came to New York. And it was a week-long party. It was great. So that's how I came to the States.
You landed in New York? Or?
Actually, I landed in Hoboken, which where this whole America pier was. And I was shocked by Hoboken, because Hoboken is a slum. And my idea of America was Doris Day movies. And that was not I was shocked. I was shocked by New York, which I loved, but I was surprised by how unclean and disorderly it was, which was great.
Did they arrange housing? How did this work?
No, but they gave me a fellowship.
And so you had to go find housing?
Yes, but at the time it wasn't like now. I mean, I found I had an apartment by myself in the village on a student's stipend. In fact, on a reduced student stipend, because American students got more than foreigners.
What year is this?
This is 1962.
You started Courant.
Yes.
What was it like?
Well, Courant was a ball. I mean, Courant was wonderful. It was a magical place. I loved New York. I loved Courant Institute. I remember sitting in the classroom and thinking to myself that for the first time in my life, I'm taking a class in something I actually want to know. And it was wonderful. The people were great. I mean, think of the list of people. Peter Lachs, Joe Keller, Kathleen Mowitz, Garbedian, Moser, Donsker. It was just wonderful. And of course, New York was wonderful. The anonymity was great. And all the great things you can go and see. The village was alive. I just love New York.
Now, you're in Greenwich Village during a time where lots of things are happening. I mean, what was it like to go to school during the day and then wander around all of that in the afternoons and evenings?
It was great. I can't describe it otherwise. And the classes were great. I thoroughly enjoyed them. When Peter asked me my last year whether I wanted to stick around as a postdoc at NYU, which I hadn't realized was possible, I was ecstatic. It was just, and working with Peter Lachs was great also. He was kind, he was helpful. It was a great experience.
How did you find what you were going to work on when you were there? I mean, you took classes like people do.
Well, I was already committed to doing things which were very applied. And also when NYU got the first big computer, the CDC 6400, I thought that was an opportunity because I already knew how to program. I had some experience with some big problems on computing, and this was an opportunity. I had an advantage. And no one around had such a big machine. So I thought that was a good thing for me to do.
Now, if I recall, it had a machine because there was this intricate connection with the Atomic Energy Commission and Los Alamos, et cetera.
Yes, absolutely.
So was that the first university to have such a fancy machine at the time?
It was a prototype, so I think it was the biggest machine anywhere. I'm not sure anymore, but it was certainly bigger than anything I'd worked on before or heard anybody work on before.
How did you start picking something to work on?
Well, I started out with Joe Keller, but I wanted to compute. So somewhere along the line, I switched to Peter, and I talked also to Herb Keller a bit. And basically, I was interested in finding a computational project. And I found one. I listened to someone give a talk about thermal convection, which is a big topic at the time. And they described some experiment. The Weather Bureau wanted to predict thermal inversions. So that when the air circulates well, the warm air on the ground rises and takes the pollution away with it. And they had this idea that if you put a thermometer on the Empire State Building at the top and one at the bottom, if there is an inversion, the top will be warmer than the bottom, and they could predict it early in the morning. But they realized that the temperature was higher at the top, regardless of whether there was inversion or not. So there was a big question which people tried to solve asymptotics, and they weren't getting any answers. And it seemed to me to be a project, something you can do numerically. And Peter gave me a bunch of papers by people trying to compute things like that, and I read them and started working. And it came up with the artificial compressibility. Can
you describe a bit more about that method?
Well, that idea is very simple. The big difficulty in incompressible flow, which of course the atmosphere is at those speeds, is that there's a constraint, which is the fluid is incompressible, and that's not a dynamical constraint. It has to be imposed on the outside, and that was giving people difficulty. And the way I solved it in this particular project is to make the equation of continuity artificially time-dependent by adding a density term with a very small coefficient, which made everything time-dependent, and then trying to see what the limiting solutions are like. But if you look at steady solutions, the perturbation doesn't matter; it vanishes. So that's the idea. And that was something of a breakthrough at the time, and it's still widely cited. So it's a good thesis.
What was the longest computer program you ran at the time?
Oh, I ran I don't remember. I don't count it. I ran very long programs because I did everything. There were no libraries available. So I did the Gaussian elimination. I did the ODE solvers. I mean, so I did everything from scratch. So they were long programs.
And did they take 10 minutes to run or 2 hours? Do you remember?
I don't remember. Well, they're quite long. Also, of course, you're not running yourself. What the system was, you took your cards and gave it to the woman at the desk in the computing center, and then she'll call you when they were ready a day or two later, and I had no idea how long it actually took. I ran cards for a long time, as I'm sure you remember.
Yes, I used them. I used paper tapes as well, but still, it's not for anything serious. You worked on this as your thesis, and what was it like then? Are you giving talks, or you're sending out papers or drafts to people? What was it like?
Same as now. I gave talks, I talked to people, and tried to publish stuff.
So when Peter said, or when they said, would you like a postdoc here, had you been considering going someplace else, or it hadn't even occurred to you that there was an afterwards?
I was assuming I'd have to go somewhere. And the notion that I could stick around at Courant was really, really extraordinarily pleasant. There are lots of great people there.
Now you've gotten a PhD, and so you're hired as a postdoc, right?
Yes.
Does that mean there's a world of, did they have a Courant instructor at the time?
No.
Did you have to teach?
No, for the first 3 years I didn't have to teach. I didn't teach. I just sat in my office and wrote programs. That was very pleasant years.
This projection method you've built now is a mathematical and a numerical and algorithmic scheme, but your goal was incompressible flow.
Yes.
What did you apply it to? How did you compute it? How did you look at the answers?
Well, so of course the problem came first. I went to a lecture. I heard somebody talk about temperature inversion. So the ground warms up the air, and
So these are Bernard convection cells?
Convection cells.
Okay.
Convection happens in the atmosphere. If it doesn't happen, then you have a problem that of inversion and pollutants remain. And the weather people were trying to predict in advance when inversion would or would not occur. And they collected lots of data which were totally mystifying because it just contradicted everything they expected from linear theory that it has existed. So the problem was to try to calculate what happens in a fluid layer heated from below. It's a big problem in meteorology and oceanography. And I heard this lecture, the guy was talking about it, and clearly he was using a method, basically a method which is used based on almost hand calculations, and clearly could not do the problem. And that's where the artificial compression came in. And of course then, which gave me very good steady flows, but then as the amplitude increases, you get less and less steady flows. So what happened there is that I was trying to calculate it. And there are lots of open questions at the time. For example, what is the structure of the spatial structure of the convection cells? The dominant theory at the time was that the stable cells are hexagonal. And it came not coming up in the calculations. So I concluded that in fact the stable cells have a different shape, they are rolls, which no one was willing to accept. And it took many years until in fact it was proved in other ways, and until this idea was accepted. It was not accepted until somebody did asymptotically. And it tells you how little people trusted computation at the time, because I think that it's fair to say that my calculations were the first ones which could be made arbitrarily accurate.
So this is projection methods plus heating terms.
Yes.
And now and the answer you're getting are geometric objects. They are rolls. Yes. They're structures like this. How did you look at them? At those days, computers were just banks of numbers and printout on papers with holes in them and that kind of thing.
Yes. And I produced my own visualization software, which of course by modern standards was terrible. But I wrote some programs which in fact painfully described figures by dots and lines. In fact, it was the early days of computing. I once saw somebody actually describe one of the algorithms I used in connection with the projection methods for solving linear systems and cutting down the labor by numbering the points in peculiar ways. And it said, didn't give a reference to me, it just said, this comes from the early days of computing. And then it occurred to me, yes, that's true. Those were the early days of computing. It's a long time ago. Then I tried my hand at a variety of flows. The goal was to go towards turbulence, but of course, all the convection, you can start from very slow, very irregular flow. You push up the Reynolds numbers, the flow becomes more and more complex. And I was trying to see what happened there. I also provided software to friends in meteorology who actually ran many of those calculations. I looked at flow in channels. I looked at a variety of standard flows, and always trying to make them more and more complex and understanding how the complexity can be overcome. If you look at what people can do today, there was no debugging help. The software was flawed. You couldn't. I wrote my own Gaussian elimination programs. Everything which went into this thing, I wrote myself.
Just out of curiosity, just so we can do some comparisons, do you remember the sizes of the meshes you used?
Yes.
So this is the biggest it could fit on a machine then?
The calculation, in three-dimensional calculations at the time, you could not fit a three-dimensional array of the appropriate size into the computer. So slice by slice had things that would be read out into memory, read from memory into the computer, processed in the computer, and read back into memory. And if I remember correctly, 20 by 20 by 20 was the biggest grid I could actually fit into the fast memory, which is preposterous. So you can't do anything on such a grid. Heroic days of computing.
What came after the method of artificial compression?
Then came the projection method, which in fact, if you look at it in detail, is just a limiting case of artificial compressibility. And that was it's an extremely simple idea.
How did it work?
Well, there are lots of papers in which people look at Navier-Stokes equations and say that, and write them in projection form. So all he does is actually implements a solution this way. And that takes care of the major difficulty which people had with time-dependent problems and incompressibility, which is boundary conditions. It's automatically taken into account. So it's not the way I came. It's not the way I came by it. I think I simply I wondered how to reduce the effect of the perturbation in artificial compressibility, and came up with some iteration which removed that effect. And then I realized that, in fact, I had implemented a projection without realizing it.
So what did people do previously? They would take the solution to the Navier-Stokes equation at one time step on a mesh, update it to a later time step, and then they'd have to deal with the fact that they had missed the incompressibility constraint.
No, the way that people did it at the time was overwhelmingly, they worked in vorticity stream function variables, which are messier, more difficult, more complicated, and very hard to do in 3 dimensions. So that was the state of the art. There was a paper by Harlow and Welch from Los Alamos who had some idea of using VP variables, the ones I used, but they didn't quite. It was an interesting paper, but didn't quite get the general case, the general construction. The way they did that constrained them to inefficient schemes and problems with boundary conditions. Still, it was a great paper because we had great progress. And I found, I think, a general formulation, which is. I'm still surprised at how much play it still gets because, in fact, it's quite simple.
When you finished it, was it one day you realized, oh boy, or was this a long, slow process when you realized, okay, this is going to work? Or was it one day, of course?
It's of course a slow process. You know, we program, right? So you have a very nice mathematical idea. Between that and something that works, it takes time. It takes patience. It takes many numerical experiments. It gets all the details.
Well, sometimes you can know the idea is right, and then you just kill yourself to get it to work. And sometimes it's a little more entangled.
But what happened here is different. I was making something else work. I was making an artificial compressibility with compensation for the epsilon work, and that worked. And then I realized it took a long time, and then I realized, oh my God, done it. That's a projection. So let me present it that way. So it was this was a disguise of something which already happened, but it took a long time. I tried my hand at lots of things in those early years in Courant. Boltzmann's equation, some Monte Carlo stuff. I was very influenced by Donsker. I took some probability courses he taught, which are great, and therefore I've always been trying to do something which has some probabilistic flavor. And but of course, the goal that became understanding turbulence, which was something I'd been interested in college. I took classes in turbulence then. And so I tried to climb to higher Reynolds numbers, and that was, of course, very difficult. The Vortex method, which came next, was supposed to be an attempt at doing turbulence, but that didn't quite work out as a turbulence problem.
But the Vortex method is returning to vorticity variables, which you had sort of
absolutely
said goodbye to in terms of creating the first set of things.
Yes. But it's different because, as you know, it's different. The idea is to try to the difficulty is you can't climb to higher Reynolds numbers numerically because the flow becomes too complex. So the idea was to try to remove the grid so you would have no numerical spatial error, diffusive error, and that became a grid-free method, and the vorticity being almost an invariant. That's the natural way to look at it. And I put a lot of work into that for many years.
If you have the method, the projection method, and now you tried it on several different examples and several different things, then what? Did you keep doing it for whiles, or did you sort of?
No, so my goal was to climb to go to turbulence, so to climb to higher Reynolds numbers. And I did some error analysis, some rigorous error analysis for the projection method or for difference methods. And you realize very quickly that the complexity of a turbulent flow cannot be, certainly not with computers of then, cannot be mastered by more and more computing power, more and more finer grids.
Well, it's still true now.
It's still true now.
Okay.
But at the time, certainly, closer. You get closer, but still, it's still very far. Yeah, it's you. There's a rule of thumb that each time you increase the Reynolds number by 1%, the computational effort doubles. So if you think how much now you have to raise it to maybe 2 to the power 100.
So this is a Moore's law for Reynolds number?
Yes.
In which every year you get 1% higher Reynolds number?
Yes, something like that.
Okay.
And you have to go, now at about 1,000, you have to go to 10 million, it's hopeless. So the Vortex method was basically, I think, cute attempt, but ultimately unsuccessful attempt to look at turbulence.
What happens next?
One day, Peter told me, well, now you have to apply for an assistant professorship and start teaching. And I said, I wanted to be a postdoc some more, and he said, no, you can't, you have to teach, because you have to start being promoted. So that's what I did.
There, you stayed there?
Yes,
okay.
Yes.
What was it like to teach? Had you done it before?
No, it was my first teaching experience, and I'm not sure I took to it very well. My first course was a graduate course in numerical analysis, and I was supposed to, the idea was to use Isaacson Keller during the first semester, and I covered it cover to cover in 3 weeks, which was not a success.
I'm guessing the students didn't think so either.
No, obviously the students didn't think so. That's okay, I taught a variety of courses. I taught a fluid mechanics course, which I enjoyed. I was souring a bit on New York. By the time I got married, had a child, it was very hard living in New York.
What year is this now?
69, 70, 71. Okay. I felt a bit claustrophobic in New York, and also felt maybe that I should go and become more independent, because there at Courant, or those authority figures were slightly overawing me. So I started thinking of possibility of going elsewhere. I got a number of offers. What I finally did is actually not take another job, but come to Berkeley on a 1-year visit, because I come here to give a talk. I really liked it here, so when they invited me for a visit, I came. And during this year, I really liked the department. They seemed to go for me. Chorin was very supportive. Smale was very supportive. I hit it off with Abe Taub. I liked the department, so asking me if I wanted to stick around, I said sure.
Between those three people,
Yes.
Chorin,
Yes.
Taub,
Yes.
and Smale, those are very different corners of mathematics.
Yes.
Okay. I guess numerics, everything from topology and dynamical systems, and then we're looking at differential geometry. What do you think it was that you did that made all of them comfortable with it, or was it an attitude they had towards applied mathematics?
I'm not sure. Chorin I didn't have any anything mathematical in common with Chorin at this point, but he seemed to think applied mathematics was a good idea, and I certainly and was very supportive. He used to ask me what I did, and I used to tell him, and he seemed to be very supportive, and that was very pleasant. Smale, of course, had an interest in computation by then. He was doing his work on Newton's method and stuff, so he had some link. Abe Taub, of course, had done all his great work on fluid mechanics with von Neumann, so that was so he had a direct interest, even though at that point he was doing relativity. So that was I felt comfortable, and I certainly liked the Bay Area and I liked the university. It was important to me that it was a public university. I had gone to private school in Switzerland, and I had conceived some dislike for private schools. So I felt that education should be public.
Did they have a good computer? Or were you saying goodbye to a fancy machine?
Yes, it was very hard to leave Courant, because Courant is a great place, and it's still the mothership of applied mathematics. It's very hard. But there's some advantage in being here and being basically in a place where there's not much applied math yet, and so you can actually think of what it should be like. And because the machine was terrible, and I had to go out and buy machine time elsewhere. I bought machine time. I had a grant from ONR which paid for machine time, and I bought some from NASA and from some private company on federal money.
How did you use it? There's no internet. There's no.
I would go there with my deck of cards.
Okay, you would go there with your deck of cards. That would do it. Yeah. Okay. All right.
Technology has just changed a lot. It's not the same. And of course, the ONR was willing to buy me a computer, and the problem was there's no one who could manage it. There was no administrative structure which was willing to do the accounting and stuff. That's how I came to LBL. Access to computing and willingness to administer a computer.
You moved from Greenwich Village to Berkeley, California.
Yes.
And you moved to Berkeley in 19...
I came for 1 year, for 71, 72, and joined the faculty in 72.
Okay, so you seem to have a history of moving to active spots of the world during their active period. So Berkeley was maybe a little earlier than that.
Yes.
What was, I think you once told me that you looked at a map once and thought that Berkeley would be an attractive place to live, or San Francisco.
When I was 15, I was living in Geneva, and I tried to ask myself where I would like to live. And the conditions were somewhere where I could emigrate to, somewhere, a country whose language I could learn, by the sea, and as far away as possible. So I came up with San Francisco, Seattle, and New Zealand. And San Francisco turned out to be possible. So I'm sure that's one of the factors which got me here, but not quite consciously.
And what was it like when you first got here?
It's beautiful. The first time I came here, I rented a car at the airport, and I thought it was so beautiful. That's before I first came here for that year. So beautiful, so also reminiscent of Israel in landscapes, in vegetation, in light, which was also important to me. So that I really like to be here, and I've been very happy here.
You spent many years in fluid mechanics. How do you think the field has changed during the time since trying to program something to look at convective flows to now?
There's been no revolution in the sense that the computing has become much more sophisticated, the methods more sophisticated, turbulence still unsolved. The numerical methods change a lot. If you look at what our colleague Peyer does, it's way above what I was doing when I last did that. But I guess the main problem is still unsolved. The people in the field have changed attitudes. It used to be so that the fluid mechanic that was easier to publish a numerical method in the paper in the mathematical literature, but not in the fluid mechanics literature. They felt that this numerics was not respectable or not accurate enough, not reliable. And that attitude has to a large extent changed, as it must, because that's, of course, the way to do things. But there's been a fast and thorough improvement of methods, but not really a revolution in the problem which is most interesting, which is turbulence.
Is turbulence solvable?
Well, I'm sure it is, but the question is how. And what's missing is some fundamental new idea. It's a mix of uncertainty, structure, and lack of structure. And at this point, you can deal very nicely with a system which is very random, like a perfect gas in equilibrium, or a system which is deterministic. But the mixture is not, you don't know what to do.
Well, I should probably be more careful about the word solvable, because I don't know what that means. But I would say
computable from first principles.
You think it is?
I think it is, but you need some new idea, which we don't have. So at this point, people try eating at the edges of the problem, but it's not making enough progress.
Is there such a thing as a problem that's just probably too hard? Too many scales involved, too many things involved?
No. The problems are too hard now, but not... Okay. My feeling is that anything which once you understand it, you can do it. And the understanding, the calculations progress together, but you need some new idea. Chaos was a new idea. Chaos explained how come you can have a random phenomenon in deterministic equations, and therefore it provided the insight. But it has not helped solve the problem, because what you can describe well by chaotic dynamics and turbulence is still laminar. Turbulence is much more complicated. So, but that was a new idea. One needs some other new idea which will actually allow you to go into the turbulent regime, and it's not there yet.
Do you think that new idea will come from mathematics or statistics, or what has to come into play?
Well, the problem of turbulence is a mathematics problem, because the equations have been known for a century and a half, Navier-Stokes equation. No one has any doubt about their validity. There can be no doubt about their validity. So the problem is solving them. And so you need to solve them, you need some good representation for the solution, some good candidates, some insight, and it's not there. But other fields in which the issue is mathematical, that you know something about the equations and the roadblock is being able to solve them. Many problems of quantum field theory, you could compute well enough. Extracts information from the theories to compare with experiment, for example. But so it's mathematical problems. And math develops, as you know.
When you came to Berkeley, were you within math, sort of the first CFD person?
To some extent. Well, Keith Miller was here already then, and he was doing CFD. I would say I was probably the first large-scale computing person. Okay. Let's say. But more came quite soon.
And then you were joined by other former Courant colleagues.
Yes. First was Ole.
Ole Hald?
Ole Hald, yes. Yeah. Who actually was a indispensable friend for many years, a collaborator. Been very fortunate that he came here. Alberto came.
Alberto Grunbaum.
Grunbaum, yes. And other people, I guess you know them.
At some point, If a finite difference method on a nice mesh is not going to get to turbulence, you then started with vortex methods, and we talked a little about those. At some point, you then sort of moved to spin systems, physics on lattices, things like this.
Yes.
Was it still about turbulence?
Well, I was also interested in quantum mechanics, and I was interested to some extent in college of quantum mechanics, and I've written some papers very early on, even still at Courant, about representative numerical evaluations of path-integral formulation of quantum mechanics. And I saw a relationship between the turbulence and quantum mechanics in the sense that I was trying to find simplified problems in turbulence to look at, and I came up with some lattice versions of fluid mechanics, which I thought might give some insight. I was mistaken, but I thought so. So there was a natural connection there. But it turned out to be the connection between fluid mechanics and quantum statistical problems is really cannot be made close enough so that you can borrow methods for one and go to the other. So this was a long slog, which I'm not sure was so successful. I wrote a book about it, which people cite, but the papers which underlie the book are very rarely cited. And so my experience was that whatever you work on, which is if you take any problem in mathematics or applied mathematics and you understand it and work on it and eventually make some progress and come up with something interesting. Turbulence is the exception. And so I think the most successful effort I made on turbulence was with Grisha Barenblatt, who came here in '96, and we hit it off, and we worked together from the first moment, and we came up with this scaling theory of turbulent boundary layers and turbulent shear flows, and also of homogeneous turbulence. And at least as far as the shear flows and boundary layers is concerned, it's obvious to me that what we did is the truth. It's a good mathematical shape. It agrees with data, which where nothing else does. But so this I like that work, but it has not been well accepted, and I'm not quite sure why.
It's hard to get new ideas accepted in turbulence in general.
Yes.
Well,
I can see that it runs counter to what people have been taught. And still, I think it's the truth.
More recently, then, you started to go into aspects of statistics and sampling and filtering.
Yeah.
What brought you there? Can you sort of give us a general view of the problem?
It started from turbulence because I started to think that maybe what I should do is try to see how people who do irreversible statistical mechanics deal with complicated problems and see if there's something that I could borrow. And I came and therefore started reading up and working with the more expansive formalism of irreversible statistical mechanics, which is very complicated. Also, I became interested in statistics, read up on statistics for some complicated reasons. And the more expansive formalism is presented in ways which are very difficult to read because it's written by physicists and the terminology is hard to, I found it impenetrable. And one thing dawned on me that in fact all it was is a formula for computing conditional expectations. So I had the first version of this idea, of this observation, and I talked about Ulehad, who came up with the correct one, which wasn't the same one I had. And so then it became very interesting to try to see, again, could we do something about turbulence with this formalism, which is actually quite different from what anybody has done. It's very interesting formalism. And then Bob Miller, who was a student here, who I knew, was asking me whether I could make any suggestions about how to do data assimilation, filtering. So it seemed to occur to me that, in fact, there's a connection there that I could. So that got me into data assimilation. Data assimilation got me into sampling, which I'd been interested in before also, but not by this good method. So I developed some sampling algorithms, and so one thing leads to another. And It's certainly the problems of which I'm dealing with now. I have some of the structural turbulence problems, in the sense that there are large, semi-deterministic, semi-random problems, which people cannot do because they're too large.
If you can frame what you're excited about right now, what can you?
I think I came up with my postdoc and students with a sampling technology, which is actually which is new, largely new, and often better than it was available. At least I think so. And that gives you a key to lots of things. And it seems to me there are lots of worlds you can try to improve the sampling in. So I'm working on problems which have to do with the sampling of spin systems, maybe make some kind of stab at quantum chromodynamics. There's a very good student working with me on those problems. I think we can make a good stab at quantum mechanics. It opens up lots of avenues. Of course, the issue is that I presume I don't have many years of work to go, so how far I'll get, I don't know. But it's very exciting to me. It seems to me that in the turbulence years, I was knocking my head against a wall which cannot be breached. That it's simply the way to make progress isn't there, and so it's exciting to me that in fact what I'm doing now is more feasible, and I can make progress in it.
You started off in an engineering school, and then you went to Courant, which is very much an applied mathematics place. And then you came to Berkeley, which is almost unique in that it's one big math department with no distinction between pure or applied or computation or logic. How much has that mattered to you?
I came here with the clear intention of keep on being applied, and I made it perfectly plain to everybody. I gave a colloquium here when I was thinking about they're thinking about hiring me, and I made very sure that they did not look what I did not look like pure math. I was talking about some problem, some Boltzmann equation, computing thing, and I spent an hour to give them the details of how to program it, and everybody looking at me a bit blank. But there's an engineering school here. I had friends among the mechanical engineers, so the math department, I was not solely dependent on the math department. I knew some of the physicists here. So you're not stuck in your department.
So it's been a very interdisciplinary thing.
But I viewed myself as a mathematician, and I thought I belonged in the math department, and I have nothing against pure math, far from it.
There are things now like computational science and scientific computing and then computational engineering and all the... What would you tell a younger person who wanted to go in this business to study?
Well, it's a good question. I worry that programs in computational science will give you not enough math so you can actually be innovative on your own, and too much practical information about how things are being done now, which you can forget because things will change. So it's a worry. It's a worry that things not in the math program do not provide a good enough education for people who want to be innovative, rather than just simply applying things that exist. But my guess is that computational science programs will become more and more common, and that computational science will separate from math eventually, just like computer science did, and will find a way to educate people who do the right thing.
I'll venture a statement, which is that of all the beginning computational areas. Fluid mechanics was one of the first, and very closely and intimately connected to mathematics, in part because of the relationship between NYU and Los Alamos and the Manhattan Project, etc.
Also because the problem is so clearly mathematical, the equations being known.
Okay, so now there's all these endless new areas where people compute, from quantum chemistry to who knows what, biology, etc. What do you think are the most exciting, not saying what you're going to work on, but what do you think are some of the more exciting frontiers for younger people in those businesses?
Look, I don't have any advice for young people except do what you find interesting. It's an arrogant thing to think that what your experience is good for others. I'm sure the young people will find their way.
You mentioned the laboratory, Lawrence Berkeley Laboratory. What has it been like in your career?
Well, of course, the fact that there was a computer access, that we could do large projects there, that we can hire people on a longer term basis, that it has been extraordinarily helpful in my career. It made it possible to do something beyond some papers, right? Segments of papers. You can actually work on a longer perspective and do large-scale computing, and that's been invaluable. In fact, it's very hard to see how I could have remained here and been happy working here if it were not for the collaboration with LBL. Because university now has hard times. It cannot provide the kind of computing equipment which I would need. Cannot provide the kind of support for postdocs and students that's needed. So that's essential. That's been essential.
It's also, I think, unique in the sense that it's the only national laboratory next to a university, and so that interdisciplinary flavor permeates the whole thing, but it's still very trying to look ahead, academic research. After you came to Berkeley, it seems there's been a real blossoming in applied and computational mathematics here. And there's many people around, lots of graduate students, faculty in other departments that do that. Can you say why? Why do you think that happened here?
Well, to some extent, it's the progress of science. Right? Computation is becoming a bigger and bigger part of lots of sciences, and departments such as chemistry or engineering hire more and more computational people. That's part of science. The world is changing. In math, in the early years, the mathematics department was very supportive of the idea of computational mathematics, applied mathematics. Again, Chorin played a very big role here because he had lots of authority and he was supportive. He was making sure that the very good Chinese students went into applied mathematics. And some prospective appointment came up, which I thought was good. He looked into it and said, yes, this is a very good idea, and people would follow him. And again, Smale was very supportive, and Smale has been defining himself as numerical, and a very different style from mine, but still doing very computational and very interesting. And therefore, the growth was natural. Occasionally, there was some of you saying that this is not really the usual kind of mathematics, but not much. So the growth in the mathematics department was I would say organic, and simply there were people in the department who were forward-looking, and there was responding to what in fact were the needs of science. In recent years, there's been a bit more voices saying that this is too unlike the standard kind of mathematics. To some extent, maybe because in fact the computational mathematics is changing, and may be changing partially away from math. It's to some extent it's a measure of its success. In fluid mechanics, when I was starting out, the big issue was how you conserve mass in calculation, which is a mathematics question. Now people try to deal with very complicated geometries and data sets and very technical issues in boundary structure, which are either computer science or engineering questions. So there's some kind of evolution there too. But I think on the whole, the mathematics department should get lots of credit for being very forward-looking and very broad in its definition of mathematics. And the lab, the growth also was this again, to some extent, there was some computational mathematics here. More people came, a connection made with other departments. The Department of Energy moved some things here. It's an organic growth. So I think it's been very good.
Well, one thing I think I've noticed at Berkeley is that some of the students one gets that choose to do applied math don't come to Berkeley claiming they want to do applied math.
Yes.
So it seems that there's lots of changing colors.
Lots of changing colors. So indeed, well, partly the reason for that is the recent years, as the number of students is decreasing, it's harder and harder to make room for people who have a somewhat unorthodox background, which is what many of the future applied mathematicians have. So that's an unfortunate event. On the other hand, of course, inside the math department, we have been viewed as a successful group and doing good stuff. So it's easy to seduce people away from pure math.
Well, I think another thing you also put your finger on, which is that now that there are so many other disciplines in which to compute,
yes,
people say, I'll go to chemistry, I'll go to mechanics, I'll go to electrical engineering, et cetera. So math as being the only home for somebody who wanted to do this has dissipated as well.
But there's a distinction between what we do in math, in the math department, and what people do in other fields, because in other fields the emphasis must be on the specific application. You become an expert in doing calculations in a specific mode, in a specific case, in specific direction. In math, you can try to look at more general issues, at things which are common to many disciplines, and which have to do with differential equations, with the basic principles of what one can and cannot compute. So there is a role for computational people in math.
It used to be that students that would come in math and wanted to do applied math, often they didn't compute at all. They were people that were more special functions or asymptotic expansions, etc. And now they often come with a perfectly skilled set of computational skills. Yes. How has that changed things?
Well, to some extent, it's all progress. It's all great. I think that the thing which makes me personally unhappy, which is that when I was in my 20s, I thought I was the world's best programmer. I was probably mistaken, but certainly had this conceit. But now every student who comes in is infinitely better than I am. So I struggle to do some of my own programming and get help from the students, and that's something which is well, it's also good, but it's emphasizes the aging process.
I felt badly some time ago when I realized I couldn't keep up, but then I felt better when I realized that neither can they.
Yes,
so the 35-year-old now is so behind and antiquated relative to the 21-year-old.
That's one of those things. Computing skills seem to become obsolete faster than mathematical skills. Yeah, that's a problem.
I think that echoes the point you were making about computational science versus studying mathematics, yes, or particular scientific disciplines. Yes. What's it been like for you working with students?
Well, I've thoroughly enjoyed it. I think that it's been one of the great pleasures here. You get to work with somebody who has interesting ideas, who's new to this, and it's an educational process. Educational process goes both ways. It's an interesting relationship. It's an interesting human relationship in its own right. It's between advisors and advisees. And I've tried to do my best I could for the students, and I thoroughly enjoyed it. And I've had many students, many of them very good. One of the nice things about Berkeley is that Berkeley made it possible. No one in the math department ever complained that students declare themselves to be future logicians or geometers, and they come here and become numerical. And it's kind of them.
You've had a large number of students, and I think it's over 60?
No, it's somewhere in the 50s.
Okay, and Berkeley had given you a prize recently, yes, for graduate mentoring and all, yes, the rest. And if I recall, many of those students wrote and, yes, were encouraging and supportive of such a nomination. Yes. Do you keep in touch with them?
I did keep in touch with many, yes.
What kind of jobs do they have? No names, but what kind of areas?
A large contingent has academic jobs. Some of them very successful at that. Other people went to a variety of industries and a variety of other things, and it's perfectly fine. That's what applied math is for. Of course, a very large contingent in recent years has gone into finance. And even though they seem to be very prosperous and stuff, and it seems to me a bit of a waste that so much talent goes into an endeavor which has no real benefits to humanity, only to the people engaged in it. But that's their choice, and that's fine. Some of the people who went to finance would have made extremely successful math professors, and it's a shame they don't do it.
So now let's return. You're trying to go to higher Reynolds number flow, and the size of the machines and the grids, et cetera, were stopping you.
Yes. So I had this idea. Vortex method were an attempt to beat those things, to beat the limitations. The first idea was to try to represent the flow by a collection of self-consistent elements, or elements as a moving average representation, in which allows you to incorporate the spectrum into each individual element. And my prototype of this kind of stuff was the Glimm's existence proof for hyperbolic equations, in which the solution is built up out of pieces, each one of which contains in microcosm the whole spectrum. So that was our try to represent the vorticity as a sum of fixed elements of fixed shape, so designed that they would contain the right correct spectrum. The second idea was I was trying to get rid of the spatial error by trying to get rid of spatial differences. So the vortex methods, basically, it's a statistical representation of the diffusion, which allows an approximation without any spatial differentiation. Technically, I modeled the vorticity equation as a Fokker-Planck equation, and then looked at the corresponding Langevin equation. So that's a method. And then I had the problem of boundary conditions, which are satisfied by creation of vorticity. It was a nice calculation. It's a viable method of calculation, which still has uses, because when the computational elements have a physical interpretation, you can build into them parts of the solution you know. And at that time, it was actually going to much higher Reynolds numbers than anybody could. But technology has changed, so I'm not sure that it's a general-purpose method at all. But it was an interesting try, and I did some other things with it.
This is a very different method from what you'd been doing before and what others have been doing before. I mean, you were talking about Eulerian methods for so many years, and then all of a sudden you've switched to this Lagrangian view of the world.
In mathematical circles, it was very well received. In engineering circles, they were unhappy because it's a delicate method. It's not so easy to make it work. But it was interesting. When I realized, in fact, and I come back when I realized, in fact, I could not go to the turbulent regime, I tried to do something else with it, which is try to use it as a modeling tool. In statistical mechanics, very often the large-scale structure of a problem is independent of the detail, provided some global quantities are in good shape. So I tried to make vortex models of turbulent flow, in which I build conservation laws and entropy inequalities and other things which are usually useful, and try to see what I would get out of this as far as the statistical mechanics of turbulence go. And it was not empty. It was difficult. And of course, it's nothing there is a proof. But I had some nice stuff about differences between quantum vortices and classical vortices, and also some stuff which played a bigger role later about the spectrum of turbulence. Much of turbulence research goes into trying to figure out, or theoretical turbulence research, trying to understand why is it that the Kolmogorov spectrum of turbulence is inaccurate and there are corrections. And there's a general theory that that the corrections come from intermittency effects. Always struck me as an odd idea. Intermittency is synonymous with turbulence. It's like saying turbulence effects are like correction, but never mind. But I made a model which got me a Kolmogorov spectrum for very large intermittency and correction when some smoothness was allowed. And no one believed that. People still don't believe that. But it had importance when Grisha Barenblatt came to Berkeley. Because when I met him, the first time I met him, we talked about turbulence, and he actually had reached the same conclusion from a totally different point of view. Very much a minority view. He was the other person in the world with the same view. So then we started working together, and we produced, in particular, a theory of turbulent boundary layers based on those notions. Turbulent boundary layers are very important. They describe how turbulence impinges on solid bodies. Turbulent boundary layers are in the atmosphere near the ground, in hurricanes near the ground, on airplane wings, and it's important to understand them. And there has been a scaling theory for about a century, which is the so-called law of the wall, which is taught to engineers, to physicists constantly. And if you look at the comparison of the data, you see that it's terrible, that you have a cloud of data and some line on the side. And people accept that as a verification because they don't expect turbulence to make sense. Our theory had actually fits the data perfectly fine with an experimental error. And I'm sort of semi-surprised that it has not been more widely accepted. I think I know why. I think that if you think about the implications of if a theory is valid, the implications are that much of what people assume about turbulence is incorrect, and people are not quite willing to accept it. But still, I was very happy about this work, and I'm sure that in time this will be accepted, because obviously, to me, it's obviously the truth.
Do you think people have a handle of any sort on turbulence?
Well, there's no real understanding. I think that the people have some general ideas of how one should deal with systems with many degrees of freedom, which come from other fields of physics, but no one knows how to implement it in the case of fluid mechanics. And at this point, nothing really fundamental is known.
Do you think it could ever be known, or is this?
It will be known. What's missing is some idea, which is going to help, some new idea, some insight, something which will unfreeze the problem. But there's no doubt about the equations that you have to solve, and it's a well-defined mathematical problem, and it will be solved. Unfortunately, not by me.
So in the same way that projection methods took off and people were using them around the world, it's true that lots of people have been using vortex methods. I've used them in places, lots of others have.
Yes. Yes, in fact, some people have done some very nice. There are lots of applications, in particular to combustion, which work very well, in which you use vortex methods with modeling. Ahmed Ghanim at MIT is a good example. My former student, Peter Bernard at Maryland, has done some fantastic calculation with vortex methods and got to very high Reynolds numbers. But it's still the mystery of turbulence persists. So I think it was progress. I think that it's an interesting idea. I think that it has some future as a first step in some kind of systematic stochastic approximation of turbulence, but it does not solve the problem. In fact, nothing solves the problem.
So my attitude would be, if one uses finite difference or finite element methods, you're stuck by the resolution of the mesh because it's an Eulerian method, and because of that, your situation is you're over-smoothing and you're under-resolving what's really going on. In vortex method, it's almost like the exact opposite is happening. You're following everything, and the price of following everything eventually comes and hurts you.
Yes. Also, of course, there's a flaw. Vortex methods assume that the vorticity can be described by coherent structures. And one of the qualitative analyses I did in a simplified model actually proves that this cannot be done. That if you have a consistent use of elements of more or less constant structure, as the energy cascade proceeds, you must violate either conservation of energy or conservation of mass. So you cannot have a completely coherent description of turbulence. You need some kind of superposition of coherence and some kind of incoherent noise. And that's the difficulty. People know how to deal with incoherence. People know how to deal with coherence, but how to deal with a shifting balance between the two is at this point not known. But I have no doubt it will be done.
In problems like turbulence, and in fact in many areas, there's more and more data being collected. There's bigger machines to store things, there's accessibility to lots of information. What do you think one can glean from this information in terms of trying to understand some basic mathematical issues?
Well, as far as turbulence is concerned, the answer is probably very little. I think there's a practical question. There are lots of practical questions. You have lots and lots of data. You may want to draw from them practical conclusions about designing aircraft or boats or stuff without necessarily, well, there are lots of techniques nowadays which basically allow you to take experimental data and interpolate by them for practical situations. And that's a useful enterprise. It's a useful endeavor. Not one which I'd be particularly eager to work in, but it's useful. But the general issue is the one of understanding. For example, suppose you could do a brute force calculation. Forget about data from experimental world. Suppose you could buy a large enough computer. It's not anywhere in the future, and do a sufficiently refined calculation so in fact the output looks like turbulence. What have you learned? And the answer is nothing. Because it's no better than trying to make wind tunnel and look at the turbulence. You look at the turbulence and there's not much insight in there. There are exceptions to that. There have been a collection of experiments, in particular at Stanford, distinguishing what kind of structures exist in turbulence. It trying to simply photograph it well enough to suggest possible structures and possible ways of representing turbulence which are more efficient than other representations and which give you some insight. It's all in the realm of the possible. The big discovery from experiment. Okay, so the experimentalists think that they have discovered organized structure in turbulence, which in fact, if I may say so, I saw several years before that in the Vortex calculations, to some extent. But of all the large vasts of amount of experimental data about turbulence which have been accumulated, there are very few which give you some insight. And the issue is insight. There's also this big trend in science that you really can make predictions without understanding anything. As you mentioned some things. Neural networks, weather forecasts, for example, which make no attempt to figure out what the mechanics of the atmosphere are, or what the forces at play are, and what's important. You simply collect lots and lots of data, and then you write a program which classifies the data, and when in a given situation finds the set of data which is closest to what they're seeing, and makes a prediction on that basis. And that gives rise to philosophical questions. What's understanding? I had lectures I used to give about the limits of understanding. In classical Newtonian mechanics, you have a feeling you understand. Bodies which attract each other at a distance make sense. You can imagine some imaginary rope connecting the sun and the moon and Earth, and you have some understanding. Things attract each other. So it has a heuristic value. Quantum mechanics, it's a set of rules, abstract rules. What do you mean? No one understands quantum mechanics. You get used to it. You learn how you used to calculate. You understand. But it's not the same understanding as an understanding of classical mechanics. You have an abstract theory in which you say, and what do you mean? What does it mean to understand? So you may actually, somewhere along the line, get the ability of reproducing turbulent flow by computer program and matching data, and that will be an achievement. And this will be understanding. It's not so clear. And actually, I'm doubtful that you can actually achieve that kind of imitation of nature without actual insight.
Well, I think there's that, and there's also that the point to a mathematical model is not simply to be able to predict data predict solutions that's within the range or bracketed by the data you have, but actually to go extrapolated far further outside a place where there isn't information. And I think there, the notion of pattern matching immediately is seen to fail.
Yes, absolutely, I agree with you.
There is a difference between an answer and understanding as to why that answer is correct.
Yes, I agree with you entirely. Certainly, I 100% agree. Except the understanding is becoming generalized, and where does the boundary lie between the notion that between you being able to say that you understood, and your ability to write a computer program that produces something which looks like what the thing you're trying to understand? That's not clear to me.
Well, there's the Yogi Berra quote, and I can't get the order right, which is you can observe a lot by seeing, or you can see a lot by observing. But whatever. I mean, there's a reason to look at the real world and see what comes out of it. That's one type of understanding.
Well, the work with Grisha, certainly that model of turbulent shear flow came out of the looking at data. I mean, people made measurements and Reynolds numbers higher than before, and this was something unexpected, and the question was, how do you explain that? And so we came up with some explanation. The explanation is not, it's a scaling explanation, so it's not really a mechanical explanation. It's not a full explanation, but it's a mathematical model. So data help occasionally. But it's tricky. I mean, it's not clear-cut. On the whole, I think that data don't give you explanations. But maybe they raise questions, but not explanations. But it's not absolutely clear-cut. No.
It also is a surprise to people to discover that data isn't always true.
Yes.
There's errors, there's misunderstandings, there's inaccurate experiments, there's poor measurements, there's all sorts of things. So,
well, in fact, this work I've been doing of late about the data assimilation is a way to try to clean data, get data which are unreliable, and models which are unreliable, and try to conclude from them something which may not be completely false.
There's a bit of a philosophical worry in that. So if the data isn't necessarily right,
yes,
how do you find a model that will be more right than the data?
No, that's not the issue. The issue is, suppose you have a model you don't trust and data you don't trust.
So there's degrees of trust in what you're saying here.
Yes. And suppose, out of the two, can you get something which you trust a bit more than you trust either one? That's really the question. So and the answer is, well, you have to do it right. I go around giving a talk which is called Why Predictions Fail, which I try to discuss how people make predictions for economic predictions, climate predictions, stuff. So they have models which are noisy, and they have data which are noisy. And so to make a prediction, you need both the model and data. And of course, the problems of the two. So the models may not be good enough, and data may not be good enough. On the other hand, the issue of how you put models with data correctly has not been properly addressed. Just about all the software that's being used to make any kind of prediction depends on some mathematical assumption, which is, I'm not sure what, separation of scale, which justifies what's being done, which is invalid. I mean, it's valid under particular circumstances, but it's valid much less than the range of things which are where it's being used. In particular, in economics and finance, they make assumptions of separation of scale which are totally legitimate. And the reason why they do that is, of course, doing it correctly has not been fully explored, and from everything we know, it's very difficult. Time-consuming, mathematically consuming, computer time-consuming. So there's even trying to draw conclusions from data is at this point a mathematical question which has not been properly addressed and has not been solved. And so that's something which requires work. And I'm hoping to make a contribution, but of course not nearly sufficient.
You kept talking about turbulence as in trying to do some methods, deciding it wasn't going to do turbulence, and then simply saying, okay, this is a great method to go on in life, now I want to go back to turbulence. What was it that so attracts you, and why do you think this is so important?
First of all, turbulence is all around us and in our bodies and in our environment and stuff. It's an important question, what's going on there. It's a purely mathematical question. It's a question, the equation unknown, and we seem to be unable to extract the information from the equation. So this is something which is an extraordinary challenge. Idea is missing about something which is all around us, and we should be able to understand. So it's annoying, it's irritating. It's also, okay. Turbulence is fascinating. You can go look in the ocean, look at the water flowing, the variety of structures which are there are very interesting. It's also a prototype of other things. Much of our lives has this structure of a mix of structure and randomness. And that's what we live in. That's what makes our life interesting. If there were structures necessary, if there were no randomness, it would not be interesting. If you could understand something about turbulence, you could understand something about maybe some other philosophical questions, which we have no way of dealing with. And that makes the problem extremely interesting.
Why do you think it has been so hard?
It's very hard because, again, we have no machinery for dealing with things which are with ephemeral, with what is the turbulence, which is an array of randomly generated ephemeral structures. There's no description of that which works. It's not. People thought of there's all those things about fuzzy sets about which you can't make not applicable here. The other problems which have a mixture of disorder and partial order as in spin glasses, but it doesn't seem to. I spent lots of time with that one, but doesn't seem to have much to do with turbulence, and there seems to be no prototype.
This is true because you get the idea of organization coming from disorganization reemerges with different names: emergent systems, global structure dynamics, etc. And there are things like Zhabotinsky waves and combustion and all sorts of places where it looks like small-scale things organize themselves on from simplistic games of life to real thing. But how come, at least to me, they never make the leap over and say something about turbulence?
Because they're all low-dimensional. The thing which makes turbulence different is that all those chaotic structures, all those emerging structures, all that mechanism of which connected with chaos has an additional, very essential factor that the number of those, that the dimension is very large. And if you think of what, for example, the people talk about, chaos theory has been successful in describing flow between counter-rotating cylinders at moderate Reynolds numbers. But anybody looking at those flows, which are in fact chaotic, exactly as chaos theory says, they are in fact laminar because the nicely predictable finite number of scales, it's not turbulent. So you have to add to this large number, the extraordinary complexity.
I think there's an even worse problem here, which is that a successful understanding of turbulence means not only do you understand how these small-scale, disorganized things interact and you get something big, but that you get something at the end that you can measure and then use to make accurate predictions, build structures, etc. And many of the models that seem to show how small-scale things become emergent big patterns, all you're supposed to do is say, great, this pattern looks big and that pattern looks big, so we're done. And I think successfully understanding turbulence requires more than simply an aha, look at the patterns, they look similar.
That's one of the shortcomings of turbulence theory, is that for practical purposes, if you really care concerned about designing things, the turbulence problem is conceivably solved. People have enough experimental data for, you talk to people in aircraft, they have experimental data and they've learned how to interpolate between them. And they don't need the theory. Except when you go, the only place we need a theory when you go into something like building a spacecraft in which we reach Reynolds numbers for which there are no data. And then you may need some kind of theory. But for most application on Earth, you can do without the theory. So that limits the interest of turbulence theory, it limits the interest of the agencies in funding it. Also slows down progress.
Slows down progress. That I don't understand.
That slows down progress because You see, anything in which people are practical people are waiting for the answers of what you do has a strong force driving innovation, driving investment, and forcing people to throw away obsolescent theories. If the clients are not clamoring for the answers, people the fact that some avenues of research lead nowhere does not necessarily kill them fast enough.
Okay, but there are very practical applications. You have a wind farm and you want to understand how the turbulence there affects whether or not you have a constant supply of energy from your wind farm, or you've got to keep a gas burner going full time anyway.
The problem is the wind farms. The problem is trying to predict the intermittency in the weather. And that, of course, is So that's a good question. But it's not obvious that people are going about it by simply using data, and it's not clear that you cannot get there by simply looking at data without any fundamental understanding.
So I think that's an example of what we were talking about earlier, which is data is fine except when you're talking at intermittent phenomena, rare events, etc. In which case, what do you do?
Well. I'm afraid turbulence theory will not contribute much to that particular problem. What will contribute to it is actually getting more and more data without fundamental understanding. So it's a tricky thing. I think my feeling about turbulence theory nowadays it's stagnating, and I think one of the reasons stagnating is that there aren't any clients clamoring for new answers.
Can you pose a client that would need a turbulence answer that won't be satisfied with data?
I'm not sure I can think of one. I think that using prior data has not been successful without also an trial and error component in designing, for example, re-entry vehicles from space or very large tankers, because the data were not available and people made mistakes and paid for them, but maybe they've done what they had to do. So I don't know. Okay. It's still a mathematical mystery. It's what's going on. Why? You look at the turbulent flow. What's going on there? How come it looks like this?
That problem appears in numerous different worlds, not just the turbulence. How does anything get organized and structure itself?
Yeah, but it's very much the same kind of problem. I mean, in biology, it's a big problem. How do structures arise?
The mathematical and numerical methodology you were building to deal with some of the harder issues in turbulence having to do with noise and statistics and randomness and all the rest, did this take you into other areas besides turbulence?
Well, it got me into data analysis and sampling. And may I describe how it went? So I was trying to find ways of describing turbulent flows, but not by describing only some of the variables and relegating the rest into some kind of noise along the lines of a vortex method. And there's this formalism in physics, the Moritz-Zwanzig formalism, which does exactly that. It basically allows you to pick some variables and derive exact equations of motion for those variables in the sea of all the others. So that seemed to be what was needed. It was also attractive to me because the world in which this works is very much the world in which I used for vortex methods, Langevin equations, Fokker-Planck equations. The first problem was to understand it. The physicists often have a very good insight into the physics and the right equations and the right proofs, having in mind what they know to be true, but not necessarily a way to explain to mathematicians. And I worked with two very good postdocs, Anton Kast and Ras Kufferman, and with my old friend Ule, and it took us several years to figure out what exactly this was. It turned out to be a statement about conditional expectations, how conditional expectations commute with nonlinear evolutions. But it's a non-trivial statement. And our explanation, actually, many people, physicists use our explanations because they're actually clearer than what the physicists wrote, because the mathematics makes things clearer. We also noticed that the mathematical problem of making predictions from partial data, which is comes in data analysis, and the problem of decay to equilibrium of non-equilibrium systems, which is what Moritz-Zwanzig is about, are the same. So that gave us some interesting insights.
Then we derived some formulas which represented marginals as conditional expectations. Conditional expectations are much easier to calculate than marginals, and that came from the more expansive formalism, and so that was this discovery. This opens the door to sampling. If you know how to calculate conditional expectations, you can sample a subset of variables and then expand, and subset by subset have efficient sampling methods.
Explain a little more what you mean by sampling here.
The problem of sampling is the problem of somebody gives you a probability density which is known, it's not something which you have to look at, which is known, many dimensional. And you'd like to find samples. You'd like to find independent quantities on the computer which are statistically independent and whose histograms converge to the PDF which you started from, the probability density which you started from. That turns to be very hard. In typical physics problems, you have these PDFs generate colossal numbers of states. A very small fraction of them is of importance because all the rest have negligible probabilities, and you don't know in advance where they are. So that's a very hard problem, and this is a roadblock in much of scientific computing, in quantum mechanics, statistics, in lots of problems. So we seem to have found the possible handle on that problem. I tried to construct a sampling method with that. It worked more or less well. I'm still working on it, and there's a graduate student working on it. But it was hopeful in some respects. And then came a former student at Berkeley whom I befriended when he was a graduate student 40 years ago. He's now become a distinguished oceanographer. He came up and came to talk about data assimilation in oceanography and meteorology. And the problem there is you have a model which is noisy. You have data which are noisy. You'd like to generate somehow, try to get something out of both of them. The standard example is you make a forecast, weather forecast for tomorrow in Berkeley. You predict rain. Tomorrow it's sunny. You open the window in the morning and you see the sun is shining. What do? Means you can't leave it at that, because if you don't do something, you have to your knowledge of the atmosphere tomorrow is insufficient. The forecast for the next day is going to be even worse. You can't recalculate because presumably you've done the best you could, so you have to modify a prediction with the help of data. So that's the problem of data assimilation. Using data and models together to reach better conclusions. That problem is reducible to a problem of sampling, and that's the technology of that. And the difficulty there is exactly the one I just told you, that it's very easy to generate very many possible conclusions, possible samples of your solution. Most of them would have negligible probability, and therefore you'll have to do a tremendous amount of work. So the first attempt we made at that used that sampling technique, which comes out of Moritz Zwanzig, came out of an attempt to look at turbulence. And I worked with Remin too. We worked for a year and a half and modified it step by step, and we got something which we call the implicit sampling, which is a method for using the data not only to draw conclusions about existing samples, but actually to sample. Basically, to get the data more intensely involved in the process, the computational process. And that's, I think, a success. That's people are using it. It's working in lots of settings, and I'm very proud of it. The next step is going to be, what I'm trying to do is use that data even better, even more. Not only to use the data in conjunction with models which somebody thought of to get better conclusions, but use the data directly to generate models. So in fact, it's a natural continuation, getting data more and more involved in prediction and in the sampling process. Of course, I'm hoping that I'll be able, once I do that, I'll be able to turn around and use that in some setting, some kind of setting of turbulence. But of course, the problem is that all that takes a lot of time and work, and I'm getting old, so I may not get there, but somebody else may.
One of the people who's doing this with you is a very good postdoc, Matty Motsford, and he's applying it, he's building it with you and also applying it to lots of areas. If I understand, it's everything from robotics to geomagnetism.
Yes. Sampling is a key issue in lots and lots of practical problems. Robotics is a good example. Basically, the robot tries to orient itself, and that's done by sampling and modification by sampling. That's the technique. There are lots of problems in quantum mechanics which are reducible through quantum Monte Carlo, which is sampling problems. It's one of those things which, for a pure mathematician, is trivial in the sense that, okay, you have a probability density function, it has samples, but the question of finding them is something which is very intensely difficult. It's a roadblock in lots of things. In quantum chromodynamics, it's a problem. There's a sampling problem. You can't do calculations because you can't sample well enough. So this is basically an offshoot of attempts to look at turbulence and computational probability.
What people at Courant have influenced you?
Well, of course, first and foremost, Peter Lax. I've learned from him a lot of mathematics, and that's obviously the case. A lot about how one goes about solving problems, a lot about how one writes them up. But I think the major impact he's had on me was actually as a role model. He was somebody. The first mathematician with whom I had some contact was Durham, and I greatly admired him. I certainly had tendencies more applied than him, but of course, there's no way I could aspire to become an upper-class Swiss aristocrat. There's no way. It's too far. Peter Lax was somebody whom I could try to emulate, and the encounter with him had a very major impact on my being able to even to work. And I'm very grateful. He was very kind to me. He was very understanding. He was very supportive. And I'm very grateful to him. I think that it was absolutely great. I had lots of contact with Joe Keller. I started working with him. It wasn't quite the topic I wanted to work on, but it's an extraordinary mathematician. His style of doing things, in which he goes and looks and finds interesting mathematics to do in very applied problems, is really quite extraordinary. The range of the things he did was extraordinary, and somebody for whom I have a lot of admiration. I sometimes regret that I've not expressed my appreciation to him enough in the early days. My contact with Donsker was very important to me because he was, somebody who was very helpful, willing to discuss strange ideas which I had here and there and taken it seriously. Taught extraordinary courses, and I think that my interest in probability owes a lot to him. I've really greatly appreciated the friendship and the warmth of the Courant Institute in those days. And much of it, and the contact I had with Kathleen Morowitz and with Louis Nierenberg was very important to me also, even though it was more limited than with the first three I mentioned from the scientific point of view, in particular because I was so much more applied in Nierenberg. But the Courant Institute, as I said, we discussed talking about this, was a magical place. Friedrichs, again, I came on the scene when he was already quite old and not quite cut around so much. But he was, he said kind things to me about what I was doing and was very supportive. One time I was invited to give a talk to the NYU trustees, and I talked about turbulence. And after the talk, Friedrich approached me and said to me that before my talk, he knew nothing about turbulence, and after my talk, he still knows nothing about turbulence, but on a higher level. And he was very gracious to us.
Now, you've been at Berkeley for 40 years, if I'm doing this?
42 years.
Wow. So what's it been like?
At Berkeley, the support of the senior members of the department was very important, and I'm very grateful to them. I had a number of people here with whom I had scientific interaction, which was very essential to me. And I mentioned Abe Daoud briefly. I had a long working relationship with Tony Oppenheim, who was a mechanical engineer with whom I wrote a paper about combustion, about turbulence, and whom I greatly liked personally. It was a shining example of a perpetual optimist working as hard as he could at all times in an intelligent way. He had a great breadth of interest, and I certainly enjoyed this company, and I really liked working with him. I had a very long, happy working relationship with somebody who came later on the scene, which is Grisha Barenblatt. We wrote a whole bunch of papers together about turbulence, and I've learned a lot about him, about scaling, about other things which I'm using nowadays quite a lot. And again, this has been a very happy, long-term collaboration. Of course, the most important range of interactions I've had were in the other direction with students, and that's we mentioned briefly, and that's been very important to me. So the range of personal interaction in Berkeley has been very wide and very rich, and of course I should not forget Ule Hald, who's been my long-term collaborator on lots of things and a close personal friend, and supportive in many ways in lots of difficult times, and basically without him, much of the work I did here in Berkeley could not have been possible, because this constant exchange, and his point of view is so different from mine. So he's tend to be much more precise and more rigorous. So he checked my wilder flights of fancy and provided me the tools to deal with lots of things. And again, I really should have put it much earlier. That's been a remarkable relationship.
Do you still get students?
I have 2 students at present, but I'm no longer working with large numbers of students, which I used to for a while. And of course, I have several postdocs. That's also a pleasure.
I know you said you wouldn't be arrogant enough to tell a young person to do what to do.
Yes.
Maybe I'll ask a slightly different version of it. You've been very successful with lots of graduate students working relationships.
Yes.
Do you have a view or a philosophy of what to do with young graduate students that you think has played a role?
To have a philosophy about what to do about students, I think it's too arrogant a thing to have. I try to work with them, I try to help them, I try to work with them, and I try to make sure that they have something that they're not simply doing what I tell them, that they're somehow or other that this is a collaboration, and that the work becomes their own. But it's something which gets to be harder to do as you get older, because the gap between you and them becomes larger. There's a cultural difference after a while, and the important step in which they see that they know more than you do about their problem, and therefore your advice is not necessarily so great. That's an important step for them to see, and it's harder for them to say to themselves, "I know better than this guy."
When you came to Berkeley and Courant are very different places. You mentioned one was public, one was private, but there's a lot of difference in terms of their size and things like that. Was that an attractive component to it, and how do you think that influenced your work over the years?
Berkeley has financial troubles, but and no longer ranks as the best university in the world. Lots of things, for lots of reasons, but still, I think probably the best graduate school in the world. It has an unbelievable range of outstanding people in a very large number of disciplines. And if you're interested in the application of mathematics, it gives you unbelievable opportunities to do various things with lots of people. So I had lots of very happy collaborations with the people in mechanical engineering. I mentioned Tony before. There were other people. There was Korkus, who was an engineer who was interested in turbulence. There was a number of numerical people there. There was Stanley Berger, which I should have mentioned, with whom I worked a fair amount. He's been interested in biomathematics, and we had very interesting exchanges and enjoyed work.
There was Den in chemistry, if I remember.
I had a very happy collaboration with Morton Den, who was in chemical engineering, I believe, or chemistry in that college. And again, the collaboration gave rise to some interesting algorithms, and in fact, some of the work on the more advancing formalism was started in the context of collaboration with Morton Den and the graduate student who came to work with us both, a postdoc who came to work with us both. So that has been a very heavy collaboration. There have been also very interesting exchanges over the years in mathematics. I had a very interesting collection of exchanges and a conversation with Kato about Navier-Stokes equations, about how the theory and the computation interact, and it was extremely interesting. I started to learn more probability from in the various courses in Stat in Berkeley. The breadth of Berkeley and the fact that the human landscape is so varied and the interest in mathematics department is so varied has been extraordinarily helpful, because you can learn lots of things by talking to people and by sitting in on courses and I've done that over the years also. Also I've enjoyed those other aspects of Berkeley which are not necessarily having to do with research. I've taught lots of undergraduate courses, and I'm not so sure I'm like such a great undergraduate teacher. I tend to be disorganized, but I've actually had very pleasant exchanges or conversation with undergrads about lots of things. And my custom is to, when I teach an undergraduate course, I tend to sit outside the building there before the classes, just sit there, and people come and ask questions. And I expected them when I started doing that to ask questions about math. But it turns out that if you open to questions and people, juniors and seniors, come and ask questions which are not mathematical, they ask questions like, how much do you make? How does it become a mathematician? What kind of career is that? Things, obviously people...
Berkeley undergraduates are not shy people.
No, right. And often, of course, many of them come from families in which there's no academic before. They have no idea what kind of career this is. And if you can talk to them, you can actually do some good, some be helpful, and that's very enjoyable. That's what universities should do. And I for ideological and other commitments, I am very much devoted to the notion that university should be something which is run by the government, and that everybody open to the public as much as possible, and not in which the people who are better off do not have too much of a leg up of the people who don't. Many years I've been an undergraduate advisor, and I pride myself in doing a very good job. You come for signatures and advice, and they get the conversation, in which you get to ask questions, I get to ask questions, they have to get to think about what they want to do, they get to ask me advice about where to apply and what's important and what's not important. I've talked to parents of students who have students complaining their parents want them to do such and such, which is unreasonable, and I told them to bring their parents to talk to me, and I've done that quite a number of times. I told parents that their ideas about what's a reasonable career are unreasonable.
How did that go over?
Sometimes well, sometimes not.
How did the students feel watching you tell their parents they were being unreasonable?
They're often very pleased. So this aspect of Berkeley, which is a large state university of high quality, is something which to me is very precious. And I regret that the state is disinvesting in education and that this Berkeley is becoming privatized. It has to, but it's regrettable. It closes the door to people. And this is something which I thoroughly enjoyed in Berkeley. I feel comfortable in Berkeley, in the city of Berkeley, not only because the climate is good and the views are nice, but because I'm comfortable with human climate.
The traffic?
The human climate. The fact that lots of people who are not necessarily entirely concerned with making money, whose views can be somewhat controversial, who are... I have strong political views about issues having to do with Israel, and my relatives describe me as a Berkeley radical. And there's some truth in that. I mean, I tend to be conservative in my personal habits, but my views are somewhat radical in lots of things. And it's something which is great about Berkeley. I certainly, yeah, it's something I'm extraordinarily grateful to have had the opportunity to work here.
So one of my feelings about Berkeley is it simultaneously is incredibly big. You couldn't possibly exhaust it. But somehow it is a bit small. You don't see very powerful fiefdoms and things like that. And there is an aspect of only a certain sort of person is willing to talk to undergraduates and teach them all day long. And that filters towards a type of person who wants to be a professor here.
Yes, I'm sure that's the case. I'm sure that it's a place where you cannot build empires. That's Berkeley. I'm glad my career has been here and not in New York. The fact that it's so easy here to have students in other departments and to collaborate with people in other departments without bureaucratic impediments is a tremendous asset. It has been an asset to me.